Now, because we have these linear functions, we can also derive relationships for what is called the half-life for a zero, first, and second order reaction. The half-life is the time that it takes for the concentration of the substance to reach half of its initial value. So this is a good visual here. Okay? Going from this point to this point, that is one half-life. Okay? The number of green molecules here has been reduced to half. So that's one half-life. Okay? In this box, I've got 8. I reduce to 4. That's another half-life. When I go from 4 to 2, that's another half-life. 2 to 1, that's another half-life. 1 to half, half to 0.25. Okay, so each is a half-life. Take the time that it takes to reduce the concentration to half of its original value. Now the half-life in a zero, first, or second order reaction is going to be a little bit different. In your notes, I've taken you through the derivation of really it's a relationship that we're deriving just by rearranging. Okay, but what I'm going to do is actually walk through the steps here so you can follow along in your notes. What we have to work from is the appropriate linear relationship for the order of the reaction. So for a zero order reaction, we know that concentration versus time is linear. This is the equation of that line. A is equal to negative kT plus A naught. Now when we're looking at half-life, we're going to call it T half. It's the symbol we use for half-life, so it's the time of the half-life. At this point, the concentration of A is going to be equal to half the concentration of A naught. So what I've done from here to here is I've subbed this relationship into this one. Okay, so A is equal to half of A naught, and I've simply replaced the T with a T half to be specific. So what we want to do here to figure out what my relationship for T half-life is for a zero order reaction is rearrange this equation. Okay, so I've got half of A naught minus A naught is equal to negative kT half. And so this is negative a half A naught is equal to negative kT half. Okay, and to isolate T, I'm going to divide by negative K. So what I have is T half is equal to A naught over 2K. So if you know you've got a zero order reaction, you know that the half-life is equal to the initial concentration divided by 2K. So in this case, the half-life depends on the initial concentration. For a first order reaction, the linear relationship, it comes from ln of concentration versus time, and it's got a negative slope of K. So this is the equation of that line. Rearranging that to ln A minus ln A naught is equal to negative KT is what we did in the first step. Now you'll remember that when we have, for log rules, if you're subtracting, so ln A minus ln A naught is the same as ln of A over A naught, and that's equal to negative KT. When we're looking at the half-life, that's going to be the point where the concentration of A is equal to half the concentration of A naught. So I'm just going to do a little side thing over here. So if I've got half of A naught over A, okay, so I'm taking this expression here and applying it for my half-life, that is really just 1 over 2, right? Because A naught simplifies. So what we have here when we're dealing with the half-life, we've got ln of 1 over 2 is equal to negative kt of the half-life. If I move the negative over, okay, negative ln of half is equal to k times t. Now negative ln of half is actually equal to ln of 2. And the way that works, you can check your calculator if you would like to. So if you enter into your calculator negative ln of half, okay, and ln of 2, you'll get the same number. Okay? And the reason for that is using log rules, so I'll show you over here. So if you've got negative ln of 1/2, that's the same as negative ln of 1 minus ln of 2, right? Because we've got a division there. So then this is negative ln 1 plus ln 2. And ln of 1 is 0. Ln of 1 is 0, so we're left with ln 2. Okay, and so we've got that relationship, and then I move the k over, and that gives me the t half. Now again, do not panic if the math is over your head. It's not really the math that matters. It's this relationship in the end. And you can, if you'd like, you can always rely on knowing the relationship and deriving it from first principles using math, or you can know what the relationship is. Now, one of the things that's particularly special about a first order reaction is that the half-life of the reaction depends only on the rate constant. Okay? It's independent of the initial concentration. And it's inversely proportional to the rate constant. Okay, so the higher the rate constant, the lower the half-life. In this example, it gives us that the rate constant for the transformation of cyclopropane to propene, a first order reaction, is 5.40 times 10 to the negative 2 hours to the negative 1. And it asks us for the half-life of this reaction. So we know it's first order. So half-life of the reaction is simply ln 2 divided by k. So it's ln of 2 divided by 5.4 times 10 to the negative 2 hours to the negative 1, and we get 12.8 hours. Okay, so that means that half of the sample will have reacted after 12.8 hours. Now in the second question it asks what fraction of cyclopropane remains after 51.2 hours. So if you want to know what is left after a particular amount of time, what you need to do is look at the linear relationship. Okay, so this is the linear relationship for a first order reaction. We know the rate constant here. And we know the amount of time that's passed that we're studying. And what we want is we want to know the fraction of propane that remains. So really what we're looking for is the relationship between the concentration of A and the concentration of A naught. So if I move, I've got ln of A, if I subtract ln of A naught, that's really ln of the concentration of A over the concentration of A naught. So I can figure out the relationship between the two. And I've got my negative KT here. Now the inverse of the ln is e to the power of. So if I want to solve for this fraction of a divided by a naught, I need to take e to the power of. I'm just going to put answer here because I don't have the value written down. Okay, that's going to give me a over a naught. And what you find here is that the concentration of A is equal to 0.06299 times the concentration of A naught, okay, which is the fraction of A that we have, the fraction of A naught that we have left over. Okay, so you can do a similar example for what remains after 18 hours, and you get 2.64 of A naught. For a second order reaction, okay, we know that it is the graph of 1 over concentration versus time that's linear with a positive slope. And this is our function that we have. If we rearrange that to 1 over A naught 1 over A minus 1 over A naught is equal to KT. And then we substitute in our relationship for the half-life. So we're looking for K of T half. At this point, the concentration of A is half of the concentration Okay, we're looking at 1 over half of A naught, which is really the same as 2 over the concentration of A. So what we have here is 1 over A naught is equal to K T half. So we have the half-life is 1 over the concentration of A naught times K. So this is our relationship. Okay, so if you're comparing 0 to first to second order, what's important is to understand the relative dependency on the rate constant and the concentration, the initial concentration. So for a second order reaction, it's inversely dependent on both the rate constant and the concentration. Okay, so what I'd like you to do at this stage is pause the video, okay, and work through these two examples, okay, and then check them with me. If you look at the bottom of the page where you see these examples, you see a chart that is summarizing the important features that we have studied in this lesson. So for 0, first, and second order reactions, it tells you what the basic rate law is, what the important linear function is. So the integrated rate law is basically the equation of that line that is going to be appropriate for that particular order of reaction. It summarizes it nicely to show you which plot you need to get a straight line for that particular order. It tells you how to find the rate constant, and it also gives you the formula for the half-lives. Okay, so this is a great chart to keep track of all of the information that has been thrown at you, all these different equations from this lesson. So that's going to be your basic go-to chart. There is also another example. You should work through that example. It will help you to identify which relationship to use and how to use your calculator to go between ln and taking the inverse of ln. And that concludes our study of kinetics.